Hello, it's Nansner of Ala North and today we'll look at another research paper, so let's just get into it. We're going to look at Ofelimos. I hope I pronounced it correctly. I asked Tim Harrison. He was kind enough to school me. So Ofelimos um, is the pronunciation of this research paper. And basically, the research paper is about useful proof of work. And before, it's been a big problem that, yeah, you can make useful work on a blockchain, but how do you prove it's secure? As we'll see, there's many things to think about when you make a useful proof of work to make it also a secure blockchain. Um, They are doing some algorithms called doubly parallel local searches, or DPLS. I think I will just say DPLS from now on. And one of the algorithm implementation is walk-sat. And I tried to research this a bit, and my understanding is like it has to be like a Boolean operation. It has to end with a true or false, and you can also like explore different spaces that you flip between true or false, and then you end up with an optimal solution that's not known in advance. So a naive example is like the toy game where you have blocks and you can only move the top or the bottom block, and your goal is to have one big vertical block with all of the blocks on them. And so if you have A in one block and then B, C, D on top of each other, you can only move D and B. And you have to find a way to get A, B, C, D as one vertical block. Um, yeah, so we will see like all of these problems and all of these algorithms, they have to have some properties, or else it's going to be dangerous to use them as a proof of useful work, because you can then attack the blockchain if you don't think very carefully about the problems you submit and the algorithms you use to solve those problems. But yeah, what an article. We will see more. So many cool ideas in this article. Um, let's start with some of the problems that plague a robust proof of useful work. So if the work is sold is truly useful, then a problem is that attackers may direct the system towards solving problem in systems that are easy for them. For example, if you can pre-compute it, or maybe if you have like an advantage in your computations, so then it becomes suddenly easier to attack the system. And in this the way they implement proof of use work here, as we'll see later with the epoch system, is you can actually have different type of problems submitted, so it becomes even more important to really carefully investigate the problem and the solving mechanisms for this, so that you are not having problems that are so easily solved that it causes security risk on the other hand. Um, and in their contribution, they propose proof of use of work that is accompanied by a thorough security and usefulness analysis. So it uses a stochastic local search, this DPLS. And here, I think the one highlight of the stochastic is that it has to have this random probability. Um, so so you can't like know in advance what's going to be the optimal solution to the problem. You have to use statistic, you have to use calculations to get there. And they call this like underlying algorithm M, and as we'll see, they will have a three-step process, like a pre-hash, the M algorithm, and then the post-hash. That's the steps of the useful work. And it's important that this M algorithm examines a given set of points in the solution space. So there has to be a solution space. It's not something like known in advance. And that it produces more and more solution space after some local exploration, like walk-sat, that flips the bytes that to see like, is this optimal, is this optimal? And this needs to require a modicum, or like a small amount of computational effort. Um, I assume this local exploration, that means like it should not be like so long to calculate that just this one block step will take too long for anyone, and that it's like will cause inclusiveness, like anyone can contribute a small step and a small computational towards the final solution. But please correct me if that's a wrong understanding of why this requires a modicum of computational effort. And they use like a doubly, that's part of DPLS, so it's like 2x the normal extent, basically the meaning. So these solution spaces are investigated in parallel. And there's threads via the M algorithm, in this case walk set. And then a scoring function selects the best one. So you could have, let's say you have a very strong computational GPU. You can run tons of threads on this walk set. Let's say this block example, this naive example of these blocks. Let's say it's not just A, B, C, D, E. It's the alphabet times 40, and suddenly have so many blocks, and your problem is to solve that all should be in one. You can do a ton of exploration of this in parallel. Should I flip A? Should I flip A30? Should I? Yeah, you get the point. And then all of these are executed at the same time as threads in the M, in this case walkset, and then you score them based on how effective was, and I guess this you could call it the move, when it comes to moving the blocks to create one large vertical block in the walkset example. How efficient was it? And this, as we will see, is like posted as part of the blocks, basically a ranking block that ranks the different solutions, and that's a really cool part of it. It's called the 2-for-1 part of the proof of work method they use. And you have to have this like moderately hard computation, so it's essential to express the hardness condition under which the basic exploration subproblem exhibits moderate hardness. And here they just state this property is necessary requirement for a computational problem to be applicable in the blockchain setting. So basically, it should not be so easy to solve, so that it causes a security risk. This is my understanding of this. And it means that it also has to be easy enough, or like a small enough computation that anyone contribute and you can have a thread for it, but at the same time it should not be so easy that it's solved instantly and causes a security risk. That's my current understanding of that. But this part is like, I think is key for understanding this proof of useful work of Ofelimos. It's and they say it here, the cornerstone protocol is its proof of useful work process that operates in 3 stages. In the pre-hash stage, a random string is generated with hashing and testing whether a small hash value has been attained, as in standard proof of work. So this is like the very standard, the blockchain lottery. You randomize a hash. Is it under the value of this target? And if you get the needle in the haystack, you can get a block for that, and you have to crunch numbers to get to this random process. And this string will constitute the random seed for the DPLS, AA parallel local search, exploration step M. So after this prehash, and this prehash is used as a seed for the M algorithm. So keep in mind this M algorithm can have many threads, but because you have this random seed, you protect against what's called controlling grinding attacks. As this string will constitute a random seed for the DPLS exploration step and will be essential for controlling grinding attacks. When the exploration stage terminates, so You have calculated one step and explored your solution space. You post, or there's a post hash step that determines what, with a single hash query, whether the result value qualifies as a proof of useful work. And this is essential for security, since it forces an adversarial miner to seed the computation with a randomly selected seed and learn that a successful block can be issued only after the exploration step M is complete. And they point out that doing this just like naively will cause two major disadvantages. First, a number of useful exploration steps will go to waste since they won't lead to a block. So, like many times you will have a hash, it will not be the needle in the haystack, the lottery. You are using a lot of computational, but it will not produce a block. And second, adjusting the hardness of block production. So suddenly there's a lot of GPUs online, a lot of guessing on the hash, a lot of solution spaces being crunched. That it will then impact the usefulness, since miners will spend too much effort trying to find such small hashes. So the target value will be lower and lower for random seed, and again, a lot of computation in the M algorithm will then be wasted because you will not update the blockchain with a solution. So here they solve this by two methods. They have this scoring function, and the miners publish the best value that they have produced based on all of the post hash attempts. And in this way, progress in the DPLS computation is not lost. And the second part of this, like you have this scoring rank, but you have this 2-for-1 proof of work mechanism. And it allows two types of blocks with a single hash attempt. It could either be an input block in case it's inserted in the blockchain as a transaction. So let's say you're under the hash of the target, you gotta do some calculations, you include the transactions, you produce a block. It's a very traditional proof of work way of doing things. And then you have this ranking block, which also extends the blockchain, and it can contain any number of input blocks. So it could contain one ranking block with the ranks of the different solutions, could also include transaction blocks. Or, no, that's not correct to say. It can include these input blocks. That could be transactions, is correct to say. So the DPLS computation will be sped up proportionally, so the number of these ranking blocks, I guess, will be extended a lot faster the more and more join the protocol and do this number crunching. And that this way you have this proportional speed up with more and more miners joining. And the ranking block production can be maintained steadily as required for the security of the underlying blockchain protocol. In this way, the more real-world useful problems instances are submitted to the system. And as we will see later, you can even have like different type of problems submitted in like a piping method, where one epoch you're doing one problem, the next epoch you're doing another problem, and you can use these different types of blocks to read where is the progress. And or you can even like see like, oh, maybe I submitted not efficiently a problem, I need to redo it because the solution space is not improving as fast as wanted based on the calculations. Or you can see that, oh, we have found a solution we are satisfied with, and you can set this in advance. So really it's like very powerful to have this 2-for-1 proof of work mechanism. And the other part is like this usefulness metrics. Like when you do this type of theory, you also have to measure it, like and they suggest two ways of to measure the effectiveness and usefulness, or the effective usefulness, sorry. The first one is to ask how good is the blockchain execution as a DPLS engine, so you can compare it, let's say Walksat without the blockchain and Walksat doing the DPLS engine search. And another part of the paper, they compare it like with a virtual machine running this DPLS. And then you can just measure this by the ratio per unit of time of the number of steps that the blockchain protocol spends in DPLS computation compared to its total number of steps. And that's a beautiful and simple way of comparing. And you can get an overall metric with the overall metric of usefulness. So the time in the engine and the time using the algorithm. Um, in the WhatsApp, the problem they are working on, they are actually working on like a blocks world planning, a well-known hard problem in AI, and which there is an abundance of public sets for. And as I said before, you can do like this block example that you have to have all of the blocks in one vertical row. That's an example of what's that. And just like this fact that they are looking at usefulness, they suggest that this could in the future be a very exciting research direction to look at from an algorithmic perspective, as it's a way of measuring effectiveness. Um, and basically, like, that's so important for research. You can actually see the optimization executed collaboratively in a public verifiable manner on the blockchain. So if we start to implement this in a lot of proof of work, we can really grow exponentially the knowledge of different algorithmic searches or other types of algorithms. Let's see, what else did I want to highlight? Oh, here is more about this like moderately hard DAG computation, like why this is important. As explained earlier, an important aspect is that the state updates in doubly parallel local searches are performed in a distributed way and without much coordination. Moreover, the parameters of the computations performed will be possibly influenced by the adversary in the sense that he may try to post a client problem to be solved only with the purpose of subverting the underlying blockchain protocol. As the security of the blockchain depends on the hardness of individual computation of M, you must guarantee that they remain moderately hard even when the parameters are chosen maliciously. That's okay. So yeah, it is what I said earlier. Like you have to have a computation that has to have some. It can't be that easy that it goes that it sacrifices security, and fail safe in all of these proof of use of work is that they have to guarantee that the hardness of individual computations of this M algorithm remains moderately hard, even when parameters. So I guess the naive example is the blockchain, the blocks on as a vertical stack. So if you do it super easy, you don't have 40 or 200 blocks and a very hard problem. You make it super easy, one block, and how to get all of them vertical. You will solve it in a single step, and that should not be possible. What else? So some of the, again, let's repeat some of the security consideration. So no grinding, and here it's explained what is grinding. The adversary can gain mining advantage by cherry picking exploration steps of low complexity. So yeah, again, as the naive example, this block search. So you pick only the super easy ones where there's only a few steps to do. So it needs to have pre-computational resilience. You cannot know in advance and compute in advance the solution. It needs to be adjustable. So the more mining power is applied to the network, then the target hash needs to be reduced so that, yeah, it needs to work as a normal proof of work blockchain. It has to have efficiency in the searches, in this case, AA parallel local searches. So it needs to have frequent updates. Results about new points explored are published relatively fast. So again, maybe I'm a bit confused on what the ranking and the transaction blocks, who of these are doing the updates, but I believe it's the ranking block that does this. The ranking blocks ranks the different solutions. That's my current understanding. So importantly here, like, this happens in parallel. Like, you can have ranking blocks even while there's no current hash under the target. That's the traditional block. So these ranking blocks will continue to extend the blockchain. So it's more frequently updated. It has a small overhead. I think I read in the article it's 4K or something like that. And it has to be the computational overhead of integrating exploration algorithms M into proof of useful work is small. So again, the higher level of the protocol will be very similar to Bitcoin. Blocks are chained together by referencing each other by hash, and during each round, the miner selects the longest chain from his view and tries to extend it by a block. And the modification is that it's replaced by a proof of use work and a 2-for-1 proof of work. You have these transaction blocks and these ranking blocks. And the core of the mining algorithm consists of applying the exploration algorithm M, and it's the useful part of the proof of useful work. And you defend against pre-computation by prepending by hash the candidate block. Oh, so this is also why we have this pre-hash. So also because it becomes the random seed for the M algorithm, this also defends for against pre-computation, because you cannot know in advance what is going to be your random seed, or it's much harder. You'll have to guess or pre-computate for all of the different random seeds. It makes more sense now to me. As every time I read this article, I start to understand it more. So this is just my try to communicate a bit about and to facilitate interest in this very cool article. Yeah, what more? They also have to reduce the mining success probability below the success probability of hashing against this target hash. One possibility to address this issue will be to further lower the target to make pre-hashing as hard as required for ledger security. So, like this pre-hash, the target for it has to be lower and lower and lower, and it's harder. You have to throw more random guesses at it or to get a random seed. But this will come at a big loss in usefulness, as miners will spend most of their time performing hashing. So they will be stuck in this pre-hash, and all the M algorithms calculated will be wasted because they will not produce a block for it, and it will not update the blockchain with new solution spaces. Instead, we have the miner feed the output of a M into a single round of post-hashing. So that decides against the threshold T3 whether the block is eligible for publication. The second threshold adjusts the overall mining difficulty level required by the security analysts to guarantee good and secure blockchain characteristics. Note the additional effect of post-hashing to adapt mining difficulty. The miner only learns whether a proof of useful work attempt is successful after executing M. The computation cannot be cut short to speed up block creation. So this is part of why they sandwich it into a pre-hash and a post-hash. So the pre-hash is there to protect, to make the computational, not like you can't pre-compute it. The post-hash is for adjusting the target difficulty, and you still get to have all of this useful work because you can update with the solution in this ranking box. And they also don't want the situation where the miner waits with its update until he mines a block, as I said. So for this reason, we incorporate a 2-for-1 proof of work to allow for the publication of different types of blocks, so-called ranking blocks, which are standard Bitcoin blocks at higher difficulty, and so-called input blocks of low difficulty, which are not part of the chain, but rather handle like transactions to be eventually referenced by a ranking block. Oh, so maybe it's actually the opposite. It's the ranking blocks are the standard proof of work blocks, and the input blocks will be referenced by these ranking blocks, but these can also post updates on the calculations in the M algorithm. You learn something every day, every time I read this. And here is like I guess a figure trying to show this, and like how the last part, the snarg or the succinct non-interactive argument, is small proof size and small statements and witness size compared with the calculation. Basically, you can summarize it as being a very efficient way of summarizing the proof. And this snark will then be a ranking block or an input block. And of course it has to be small and efficient, because if not, it will affect everything like propagation times on the network and such. But again, you have this nonce or this random hash. It becomes a seed for the M algorithm. Then you have this post hash, and if you are under the target, you post a snarg that's either a ranking block. Let's say you also are under announced T1, then it becomes a ranking block. And if not, it's input block. Pardon. It's if it's lower than the target 2, that I guess is a combination of this and this, then it becomes a random block. And if not, it becomes an input block. And if the target value is not under the post hash, it stores the best run of M and repeats the process. This probably, if you look at this, this is the key to understanding the whole proof of useful work implementation of Ofelimos. And then they start to talk about, and for me this is like mind-blowing, that they can actually have multiple instances of problem solving in the blockchain. That is, it's so cool. So you can want to extend it or stop it, and based on the quality of the solution found, you can restart it with different parameters, and they do this with pipelining. And the way the pipelining works is that you divide into epochs, and you can then in the first epoch assign problem A1, and then the second problem A2, and so on and so on. And interestingly, pipelining also helps to deal with input block denial of service attacks, while at the same time allowing miners to consume unsettled input blocks during mining, thus boosting the performance of DPLS. So really, really powerful stuff, that you can have different algorithms, and just imagine how hard it will be to attack something like this. You don't even know in what will be the next algorithm. You will have to really, really customize an attack against this. So I really think this is one of the cool parts of doing this in a pipelining way. And then the incentive structure. So if you are a client who want to submit a doubly parallel local search for an A problem, the processing will lock phones for executing the algorithm in initiating a reward pool. I guess you can do this as a smart contract. At the end of each epoch, the contribution of each miner towards solving a particular instance A will be measured as the fraction of input blocks they contribute out of the total that is directed to that instance. Using this metric, miners will be rewarded proportionally from the reward pool of each problem. Super simplicit and super elegant. Rewards are not distributed only when the problem is found, but proportionally as you advance in the solution space toward a final solution. And this mechanism relies on the 2 for 1 as proof of work, and the fact that any set of miners will produce a subset of updates roughly proportional to their computational power. And that way it's a fair protocol. And one part of this, I guess, is also that the computational, like each thread for doing this has to be easy enough that anyone can contribute. Um, let's see. They also discussed this type of attack called griefing, where the miner does not gain anything by doing it, but is still doing it maliciously. And they say about this, even though dealing with such attacks is beyond the scope of the present exposition, we note that it's possible to assess blocks for such griefing behavior by statistically contrasting the best claimed update to the winning update associated with a small post hash. So let's say you don't want to, you are sabotaging on purpose the useful part of the work, putting in crappy usefulness, but you throw a lot of computation at it and you randomly get the low seed and low hash, so you're under the target values and you win the blocks, but the block solution part where you did the algorithm is crappy because you did it on purpose to make it bad. You could compare then this winning update with the other post hashers and see if they're effective. So there's a way to stop this type of attack. And another important part is that they have a default algorithm that the blockchain defaults to bootstrap it, and also when there's no new problem by a client that's sent to the blockchain for execution. So the default way is to pay within inflations of the blockchain, its cryptocurrency itself. Let's see if there was anything else we should mention. Yeah, I think that's all for this. It's a fair long video already. Again, hope you enjoyed it. And the one part I probably got wrong in the start is this ranking versus transaction block. So ranking, I guess, is actually the regular proof of work, and these ranking blocks can also reference input blocks that can consist like solutions, and is another form of block that's only included in the ranking blocks when you are under the target hash rate. So apart from that, I hope we this helped maybe have a bit understanding for Ofelimos. And I have to say, like, seriously, the research done by OHK, it's so far ahead of all of the other things I'm researching. I really enjoy reading research papers, and yeah, I want to continue looking at more and more IOHK research papers, as it's so cool. I learn something every time, and their ideas are novel, and they are proving it with the math. And yeah, just imagine how much better it is for the world if all of this energy and computational power we currently are throwing at Bitcoin, for example, could be then replaced with useful computationals. So powerful stuff. And yeah, that's all from me from this article. Thank you.